Can you hear me when I talk like this? Does this work? Yes, okay, good. Thanks. So now we can move that one away. Smoothly. Okay, welcome back, everybody. Sorry, this is annoying, so I need to, no, I fix this typo later. So this is, we're of course in 2021. So welcome to this lecture. I think it should be the 7th lecture or so now. And before I go into the sort of last part of the knowledge-based or the logic-based agents, I want sort of a quick check in how things are going, whether everything's all right, whether we can do anything differently or better or both, or so. So general feedback question: how are things going with this course, but maybe also more generally on with the combination for the bachelor in general. So does anybody have anything to say in general here? Yes.
I just want to have a question related to the exam.
Yes. Yes, sure. So there's a question related to the exam.
So I'm curious if we need to know any Schnapsen rules, or if there's going to be anything related to Schnapsen, or just the algorithms or whatever.
So the question is whether there's anything specific to Schnapsen that needs to be known and understood. No, there is nothing with respect to Schnapsen. You need Schnapsen for the practical assignments. So that's sort of the basics of and some of the ideas are explained with Schnapsen, but there will be no questions about about Schnapsen. Yeah.
Regarding the date of the exam, still not sure if it's going to be Christmas Eve or is it settled?
That is settled, and if you look in your schedule, you will see that it's. So the question was, sorry for the people at home. So the question was whether the exam was still scheduled for Christmas Eve, but no, we've preponed this, if that's a word, to the week before on the Thursday. I think it's the 16th. So please check it in your schedule, and it should be on the 16th. There's one more question here. Yeah.
Do we need to focus on the working group exercises or the assignments?
So the question is whether you need to focus on the working sheets from the sort of theoretical material from the working groups, or whether the questions will be about the practical, and they will be purely about the working groups. So the working groups are to prepare you for the exams, and the material that's discussed here in the lecture. So you need to know the stuff, understand the stuff from the lectures. Yeah, but there will be no specific questions about the assignments at all. Yes, there's one more question.
It's not related to the exam, but I'm curious if they're gonna shut down the university later, like if they're gonna move to if you have any idea of what's gonna happen or when it's gonna happen.
So the question is whether I can predict the future about, and more specifically, whether I can predict the future about closing down the university. It is a tricky question, and my guess is probably as good as yours. The attempt of the government is to avoid this by now sort of shutting down parts of the society and having this work at home rules. The universities have a relatively high degree of vaccination also in the student populations. So there was a test done by the WHO, I think some sample test, and I think we had more than 90% of the students being vaccinated, which in a way doesn't make us one of the high risk places. And I think up to now the behavior of students is and stuff, I have to say, is very well, is very good. So I think my guess is that the rules will not be sharpened and more stronger, because I think the risk that this the damage that this corona has done in the past years to the students, particularly the first year students, but also in principle everybody, about the mental health, has been recognized now by everybody. So we all understand how difficult this situation was for everybody, and still is. And I mean, most of you have either already studied or have been in the last year of high school. And the toll that this takes on your generation is recognized, I think, in the society. Surely here locally, we all understand how difficult this is, and we try to do our best to support you there. So we have really loads of extra activities. We have extra student advice. We have before in the last year, we tried to organize social activities when it was started to be possible. So we really try to do this locally, our best to support you. But I also think it's politically recognized that the damage that would be made by closing down the universities would be extreme. And as I don't think we are a high risk place, even though we are close together, because the vaccination rate is relatively high. My guess is that unless the numbers also at the university would go high, the infection numbers, that we might be safe and not close down. But a lot of it depends also on our own discipline. So if you don't feel well, stay at home. If you know someone who had been infected, stay at home. We try to offer everything online, also at the best possible quality. So stay at home if you think you might spread. If we get a big infections at university level, we might have to close down. But as long as the situation is relatively stable, I think we have a chance to stay open. It was a long answer of a guess. So of course, I don't know anything more than you know. So there's one question in the question answer before I come to you. So the question in the question answer is, do we get the rules for clause normal form? And the answer is yes. I answered that yesterday in the Discord chat. There was the same question. There is a formula sheet that you will be able to download during the exam, which will have these transformation rules. And I also posted this formula sheet from last year on Discord. So if you check out that is what people got last year. And I think this is also the only thing you need for this exam, but you don't need to learn those rules by heart. And for this one, I think it's just these few rules that you need to have. For the next exam, the formula sheet is far longer and more important. Okay, so this was the question in the chat. So you had a question in the room? It was the same question, yes. Okay, so then I have a question to the people in the room here, and I thought I make an official poll or something, but now I just do it by show of hands. And please just show your hand. I don't only want 3 people showing their hands in total. So just give an honest answer. Who thinks that this course goes too slowly in terms of content? Okay. Yeah. Who thinks it's going too fast? Okay, so that's about, so the too slow people were about 1%, or no, a bit more than 1% probably, people in the room, 5%. The too fast people were probably 1/3 in the room, yes? And who thinks that it's just about right? Okay, so that's the majority. So that's mostly a question to the people who think it goes very fast, at least. I mean, maybe not too fast, but it is very fast. Do you think that you get sufficient support? That although it is, I can understand that it's hard work. So for many people, maybe no experience in programming, that it might be very tough at the moment. But do you get the support that you need? Is there anybody that could turn it around? If you don't think that you get the support that you need, can you speak up now? Okay, so I need, I don't hear any shouts in the room. So is there a slightly too fast option? That is, I think some of you also probably had that, that it's more slightly too fast than radically too fast. But anyway, let's not go down that road. There's a lot of support. That's good to read. I think by moving the exam forward, it has become a little bit more tough. Fair enough, yes, but there's really nothing I could do about this that I haven't tried. Sorry for that. There's a question in the room.
No, it's just that I want to speak. Only personally, I think it's too fast. And by the questions some people ask on my WhatsApp and my group chat.
Can you speak up a bit? I can understand you.
So for me, it's not too fast, but by the questions that people ask in our WhatsApp group chat, I feel like there are a lot of people that do not fully understand the material, especially regarding the practical assignments. Some of the things like implementing and heuristic and stuff like that. I think a lot of people find that difficult, but that's just my interpretation of what they send in our group chat.
Okay, so let me summarize for the people online that from the comments in the group chat and WhatsApp, particularly that the majority of the people who have problems with the practical part, which goes sort of very fast and expect something from them, the programming part, and they don't really know how to do this, how to start. And yeah, so is that a feeling shared by the people who raised their hand that it's very fast, that it's mostly the practical part? Is that, yeah? Okay, so let me comment on that. I think that yes, I feel like I'm taking 3 different courses. That's interesting comment. Okay, interesting. And apparently very much recognized by most people in the room. So I can see that there are 2 courses, but I don't see the 3rd one. Anyway, you might comment later. So what I wanted to say is about the programming stuff. There are different ways of learning how to program. The one thing is the very systematic way that I think you're now learning in Introduction to Python. So really one concept after the next one. But programming will always be somewhat thrown into the unknown. You will get some code base which you will not understand. You will not know what the different things mean. And diving in is sort of part of the toolkit of someone who does programming. And the feeling of being overwhelmed by some code base is something that is part of the learning process, to put it very harshly. So it happens to me every time I see a bit of code. I'm not a great coder, just let's start with that. But every time I have to do some coding, I think, oh my God, what's going on here? So this is a shared feeling if you see someone else's code or you start with some programming tasks And the only way of dealing with that is getting used to it. Yeah. So you need to sort of practice, you need to practice how to understand the code, how to do step by step. Also, when you get confronted with something relatively big. So I think the idea at the moment is that you have both, on one hand, you have the Python course, in which you have everything sort of very systematically one by one. But on the other hand, you in this course, you also see that with relatively simple means that you have about programming, you can already achieve something, and you can already change things, and you can work with complex code. And trust me, I've given this course now, I think next year it's for the 10th time. And in the end, almost everybody gets around really working with these games and the platform and doing something practically on a quite high level. And that's something that you will then recognize in period 3, where you actually work on your own code. You do experiments with your own agent that you have written. And that can be an incredibly fulfilling thing. So the ambition, I know that it's very ambitious what we're doing here. We ask a lot from you. But I hope that at the end of period 3, that you will see the reward, and that it's worth sort of getting thrown into the dark. And nobody, I think maybe one thing to help you, hopefully takes the pressure away a little bit, is that you're not judged on the quality of your code. And if you go to talk to the students' assistants, there is no way you ever ask a stupid question to them. Every question you ask is simply normal. And we also realize that there are hardly people coming to the TAs in the slots that they have free. So if you think this is overwhelming, just go to one of the TAs and say, shit, this is overwhelming. I have no idea where to start. Go there, they are there for you, and they know exactly the feeling because they've taken the course 2 years ago, and they probably felt exactly like you, and they can help you. That's what they are paid for. That's why they are there. Yeah, there's a comment.
Yeah, so just a couple of friends told me independently from one another that the TAs don't actually help you if you ask them. So I'm not trying to make an overgeneralization, but there are some occasions when you ask them a question and they don't answer you based on the fact that if they answer you that time, then you will come again next time and the next time as well. And so I feel like I'm not the one having this issue, to be honest. But I know quite a lot of people who have this exact issue with different TAs.
Okay, so that's a serious issue, and I can imagine that there are some situations where a TA says, okay, if I give you this answer now, I basically answered the question. So you always have this balance for every TA. But I speak to those TAs regularly, and I cannot imagine that there is one who says, oh no, I'd rather not answer that because then you will ask another question. This is not how TAs work, at least not those that I know. But if you have this experience, if you make this experience that you really think that one of the TAs is not helpful and purposefully not helpful, then send Jan Christoph or me an email about it so that we can talk to this TA. It's very difficult in general because I really trust the TAs as much as I can. Yeah, I don't know them very well, but I know them well enough to trust them a lot. So if you have really something concrete, please let me know so that we can address the issue.
Can I add something?
Yes, of course.
So I don't know the situation in the WhatsApp group because I'm not in it, but if you join the Discord channel, if some people just write their problems in it, you always figure something out. So we always help each other. So this is also good to build Discord thing, like it's another communication channel. It's in the comments page. So they don't.
Are you talking to me?
Yeah.
But I usually don't help people.
Oh.
Yeah, so the point made in the class was that the Discord channel is also an extra possibility to get help. And we found people here in the room who are helping, and you really see that there are people helping. And it's also the TAs who are helping there. And I saw that Franz, for example, he was active last week until Thursday, I think 2 o'clock in the night, to help some people with their problems. So make sure you try to get as much help from them. And if there are really structural problems with TAs, then please drop us a note so that we can talk to them, because that's of course not the goal of it. And I will also take the comments in the chat into account. I can't read them now, but I will have to read them in the break. Question back to, there is one question which is, I think, very important in the question and answer system, and that is what happens if you have to miss the exam because of Corona. And I think the answer that this is, I think, discussed by the University Education Board today as a problem. But in principle, if you miss an exam because you're ill, you have to take the resit. This is exactly what the resit is for. So if you miss the exam, you have to take the resit. But there is at the moment discussions about it, whether there's anything specific to be done here. In particular for a course like ours, it's a very bad situation, because then you miss the chance to split your exam into partial exams, because the resit is one for both parts. So it's a bit more difficult, so to speak. You have to learn more for one event. That's one question. The other question is, when is the resit? You have to check the schedule, and then for the course, probably not yet in your personal schedule, but if you go to Rooster.fü.nl and you go to the course Intelligent Systems, you should see a resit somewhere in probably February, first week of February. That would be my guess. Yeah. Okay. I get the answer. It's not in the schedule. I will check it, but it will be in the. It might be that they haven't fixed it yet because of all the Corona shit. So, it's normally in the exam period of exam week of period 3. Yeah. There's one more.
So when are the practical assignments going to be graded?
I think most of them have been graded, the first ones, so they're working on that. But I don't know when the results will be published, but it should be one of these days. So that's at least the ambition, but we have 300 people participating, so that's a lot of work. But I know that the TAs are working hard on that. So that was the question, when the practical assignments would be graded. Okay, so I hope you forgive me that I took the time for that, but I thought it is quite important. And I think there are some issues that I would take to address with the TAs, particularly that this feeling is not, I mean, we have a lot of time, but if they are not helpful, then all the time in the world doesn't help you. So we need to get this under control. Now let's see whether I can get my pointer up to run. Yes, so I want to take a bit more time today to take one step back about Davis-Putnam. Some of you had the working groups yesterday, so you probably did your first calculations. The others have them later today. And I want to sort of take 3 steps slightly slower, because this is relevant for the exam. So next week you have to understand it. And then there is a sort of more one step back conceptually, and that is, let's look at these kind of logics. What does it mean to have certain properties of logics? We will go in much more detail in the course logic and sets in period 4. But here's a sort of a glimpse of how this will look, and so that you understand a bit more why we go through all the fuss of defining those languages. And then I will move towards more a different kind of language, so that we can now model the game a little bit better, the game of Schnapsen, and that is using knowledge graphs. Yeah. So about the Davis-Putnam. So remember, the main idea of Davis-Putnam is that you have a set of formulas or a formula that you translate into closed normal form. So now we have the set of clauses. Each of the clauses is a disjunction of literals. A literal is an atom or a negated atom. So that was the starting point. And the way we solve this is by not going through all the truth tables, because that would be horribly inefficient. Instead, we are taking a depth search approach where we start with a partial assignment of one variable, and we extend this partial assignment more and more until we either found a solution or we explored all of them and we didn't find a solution. A solution in that case being a model of the formula or the knowledge base. And doing this in the way that I just described is still relatively inefficient. So we need to come up with more clever methods, and the more clever methods were on the first ones were that we can simplify the clause set. Because if we know that a literal is true, then we can delete all the clauses that contain the literal, and we can delete the literal from all the clauses in which it occurs in a negated way. So these were the two simplifications we had. And then we have these more powerful rules, and these are the pure rule and the unit rule. And in particular, the latter one is the one where I want to sort of, which we want to really you to understand. And that's basically, it's very simple. If you have a clause that only has one variable, then it means that this variable has to be true. This literal has to be true. So there is no other way of making the clause set true apart from making this specific clause true. And that means that you have to assign the value to make this one clause true to this specific variable. Yeah. And this unit clause heuristics or rule really makes a big difference. Then the second thing is that I came up with this stupid idea of saying, okay, let's do this alphabetically. And I always started with the A, and I assigned the value false. That's obviously doesn't make any sense if I know the domain a bit more, or if I understand what I'm doing. So this is a naive way for introducing an algorithm, but in real life, what you want is to have a more informed way of choosing the propositional variable on which you start branching. And you can do this on the one hand. You could do this by understanding the domain and estimating something about the domain. So which are the variables you think in the domain are more likely to be true or false? That could be one way. In the game of Schnapsen, is it more likely that this is true, or is it more likely that this is true? That's one way. But there are also general heuristics. Yeah, and these general heuristics are about the form of the closed normal form. Yeah, so if I have a literal that occurs in smaller clauses, it's more likely that they will produce unit clauses. And the unit clauses are the ones, with the one literal, are the ones which are very good at helping me solve the problem. They are very good for efficient reasoning. Yeah. So the smaller the clauses, the more likely it is that it's good if I start with the small clauses. Yeah. So that's very useful. And this is what this Mom's heuristic comes from. So basically, you look at the smallest clauses and you check which of the literals occurs most often in it. So either the literals occur most often or the propositional variables. That's a choice you can make. Yeah. And then you start branching in those ones, and you start with which of them makes most of them true. So you start the ones which occur more often negated or more often non-negated. Yeah. So that's the Mom's heuristic. So what I want to do now is to have a quick run through such solving procedure using first one, the stupid one, the alphabetic one, with false first. So that's the one that I introduced last week in the lecture. And then let's look at the one where we have a heuristics applied. So the one that we start with the literal, I think, that occurs most in minimal clauses. And then the third variant is that we also look at, do we start with the literal to be false or the literal to be true? So take a minute to think about what you would do and how to start this. So this is a question that you might get in the exam. So bluntly, put it bluntly, this is a question, could be in the exam.
We're talking about more heuristics. So how we would start using the non-heuristic?
We're thinking now about the first variant where we do the naive one with alphabetic N first. But in the exam, there could be the Mom's heuristic. So there's one really crucial thing is that there might be, I'm not sure yet, we might check this automatically. So the question might be asked in a way that you have to be very precise in what you return. And for that, it is essential that you read the question properly. So if I say start alphabetically and you solve the problem perfectly, but you start the opposite way, the system will give you a false. And in principle, you answered the question incorrectly. So please, please, please read the question properly. So what is the first step? So how do we begin? See whether my pen does what I wanted to do. Yeah, here we go. So what do we, with which variable do we start? P. Why do we start with P? It's the first in the alphabet, exactly. So simple it is. What is the first assignment that we give it? False first, exactly. So, yeah, okay. So what happens now to our clause set? What happens to this clause? So we now know P is false. What happened to the first clause? Just shout and a bit harder. It is true. So what can we do with the clause? Scratch it out. Yes. The whole clause goes, because if you have Q or not R or true, is true. Yeah, because something or true is true. What happens to the next clause? This one. We know P is false. It depends only on not R and Q. So what we can do is to scratch out this P. Yeah, so the clause now is simplified into not R or Q. Yes, that clear? So now is your moment. If you don't understand what I'm doing, then shout. Yes, so what happens to the next clause?
Nothing.
Nothing. What happens to the last clause?
Q has to be false.
Yeah, so I couldn't, yeah, you also said something in the back and I couldn't hear it. So you have to shout more. I don't say that very often to people in a classroom, but now it's the moment of shouting. Yeah, so it simplifies to not Q. Okay. So what's the next step?
Q has to be false.
Yeah, why? Why do we focus on Q now? It's a unit clause. Yes, don't forget, we have Davis-Putnam where the unit clause is also. So the unit clause is always before the choice of the letter. And it's coincidence here that Q is also in the alphabet. Yeah. So now we choose Q because this is a unit clause. This is now a clause where there is only one literal in it, namely not Q. Yeah, there's a question?
If it was R instead of Q, it wouldn't matter.
If it was R instead of Q, we would also go for the R. No, we go for always the unit clause always have preferences. Yeah. So the unit clause is the one that sort of helps us make Davis-Putnam efficient. Yeah. So it's an essential part of the algorithm that you always use the unit clause before anything, before you do the branching on the variable assignment. Yeah. So now which value do we need to give Q? Yes, I heard a false. Why a false? Why the false? Exactly, because in the unit clause, we can only make this clause true if Q is false. Yeah. There's a question in the back.
Before choosing Q, don't you need to check for contradiction?
Bit harder, please.
Before choosing Q, don't you need to check for contradiction?
Very good point. Very good point. But as long as I have clauses that are not empty, I know that I don't have a contradiction. Yeah. So by simplifying and as long as I still have every clause with one element, I know that there is no contradiction. But it's a very good point. We need to do that. Yes, there's another question.
So there is the not Q over there.
Yes.
And if it was Q instead of not Q, then we would take the true part of the Q in the branch.
Yes. So the question was, and that's indeed, I maybe I should have made it clearer, and in the exam, I will try to make it clearer. But in principle, you always have to do so these heuristics or these choices of which letter to branch on first is only made on after you applied the unit clause or the pure rule. So, and the pure one we ignore, but the unit one we don't ignore. Yeah. Okay. So now we have decided for P to be false. That basically means that this one now becomes true. What happens to this one? You see which one I mean? Yes, the last one. What happened to it? Yes, so it only becomes R. I don't know whether you can still see what I'm doing. I just do the crisscrossing here. So what happens to this one? Yeah, it's not R. So we can again, you can simply say, okay, we delete we do have a contradiction, exactly. But we first do this because we are a stupid algorithm. We don't think, we follow a stupid algorithm. So what do we do with the first clause? We delete Q, exactly, because Q is false, so we delete it. So what we're left with is not P here and not R, that's the second clause, and R. Oh, we did indeed, you're right. Sorry, you're absolutely right. I didn't delete it properly enough for me. Yeah. But now we get a clause which says not R and R, and we basically see that this is a contradiction. Now we get to your point, but you would see that just following the algorithm, because now we have two unit clauses. Yeah. So we have two unit clauses, namely not R and R. They're both unit clauses. So we would have to decide in this example for R to be false. Yeah, but then I have R, I have to delete it and it becomes empty. And if it is empty, it's called an empty clause, and an empty clause is a contradiction. So it's exactly the point you made, that if I make the step here, the next step would be the sort of unit clause rule on R. And then I would see that I end up with the empty clause, as it's called. Okay, so there something went wrong. We don't have to do the backtracking on the unit clause because there is no choice. We had to make it false. But I think the Q was already a unit clause, so we have to do the backtracking on the P, which was false. Yeah. And I think this is the moment where I should clean my screen, because now we do the second part of it. So this one, the false one, we've done. Yes. And now we do the true one. And we do exactly the same. So what happens with my clauses? What happens with the first clause? I scratch out the not P. Yes? Is there anybody in the room who doesn't know why I scratch out the non-P? Or is there anybody on the web who doesn't understand? Online who doesn't understand why I scratch the non-P? Please explain. I don't. Okay, very good. Thanks for letting me know. So the rule says that if I make a literal true, then I have to delete all the occurrences of the literals in a clause which occur negated. So here we say, in this choice point, we say that P has to be true. But then if P is true, what I would get here is not true, and not true is false. Yeah. So then we get or false here, but X or false doesn't make any sense. Yeah, as long as I have something in here, if this was empty, then I would get the empty clause and the contradiction. But as long as there's something written there, I can simply ignore this because something or false doesn't contribute anything to the clause. I hope that explains it. So You can also read the rule, even if you don't fully understand, but the rule simply says that if you have a literal, you can delete all the occurrences of this literal that are negated in the clauses, in all the clauses of your set. It's part of the first part of the simplification. So what happens with the second clause? Where's my pen? Here's my pen. What happens with the second one? P is now true. It's always true. Delete the whole clause. Yes. So here we say P now becomes true. And then not R or true is always true, of course. So this whole clause, which is a constraint on my possible models, simply can go because it's always true. This one doesn't change. This one is this one. And this one, what happens? It's always true. We can delete it because P is true. Yeah. So now we're left with these two clauses. And now, do we have a unit clause? No, we don't have a unit clause because they all have two elements. Yes, so now we go back to our fallback option of saying, okay, we do it alphabetically. So then we do Q and we do false because that's our fallback option. That's how the algorithm is implemented. So what happens if Q is false? Yes, so we are here. So we are here. Yes, we delete this one and we delete this one. Yes? Okay. So we are left with R, not R and R, two clauses. And we can either check immediately that they are contradictions. That's one way. The other way is to say they are both unit clauses. So I choose R to be true. And then the other one becomes empty. I get the empty set. And this is a contradiction. Yeah. So what do we have to do? We have to do the backtracking on the Q and assume that the value true Q is true. And now we have a bit of a mess here. And I can't remember what I think we had these two clauses left, this clause left and this clause left. Let me write it down properly. So we have a Q or not R, and the second one is R or Q. Yes, I think these were the ones we had before. Yes. So what happens with Q becoming true? They're both true. Exactly. So basically what we found is a model. Yeah. Namely, if P is true and Q is true, the whole thing becomes true. And it doesn't matter which value we choose for R. Yeah, that's the trick here. Yeah. So we have two models in this. The one model is P is true, Q is true, and R is true. And the other model is P is true, Q is true, and R is false. You had a question? That was the question. Yeah. Okay. I hope that helped. Let's see what now happens if we use heuristics, what that means in the first place. Yeah. So now let's go to the second variant. This is the second variant. And now we apply the MOMS heuristics. So here is my dot. What literal should we start on? I hear a Q. Someone comes with a P or an R. It's a bit like Sesame Street, I think. I've got an R. Anyway. No? Q. Why Q?
Well, it is the most occurring, but I'm not sure what minimal clauses. It's
the minimum of minimal size. What are the clauses of minimal size?
It's the most occurring in the
Yeah, so we have two clauses of size 2. This one has size 2, this one has size 2. And which variable occurs most often? So I was a bit vague on purpose last slide, the previous slide, because you can implement the MOMS heuristics on literals. You can also implement it on propositional variables. If you would do it on literals, they would all occur the same amount of times because Q and not Q are different literal. But if we say we do it on variables, then Q occurs more often than the other two. Yeah, so let's do it on variables. Yeah, so Q is the one that occurs twice. Yeah, so the suggestion is that let's start with Q. Is that clear to everybody? Yeah, so now we don't have a heuristics to say whether we should start with plus or with negation or not negation. And even if we would do this with the third variant, it wouldn't help us because Q occurs once with the plus sign and with the negation sign and once without. Okay, so we go back to our fallback option, which is false first. So what happens to our clause sets? I can delete the Q here. I can delete the Q here. I can delete the Q here. And I can delete this clause. Yep. Yeah, all clear? Okay. Now I've got a unit clause. And that's why we used Q in the first place to get to this unit clause, because now we are forced to take R to be true. Yeah. So now R has to be true. What happens now? We have not P left. We have not P left. We have P left. And this one was true anyway. So we get P and not P. So we get the contradiction and we close. Yes. Okay. So then we have on the other side, and now it's sort of a bit of a mess here. So I delete again, because otherwise we will not see what's going on. So we had started on Q is false. Oops, here we are. Q is false. That one was closed. So let's now take Q to be true. And now we have this one to be true. This one is true. Here, this one is also true. And here we can delete the Q. So we know that P has to be true. Yeah. And we found the same model, of course, and we're done. Yeah. So you see that by choosing now this simple heuristics and starting on P and not Q at the beginning, we very quickly come to a solution. And in this example, there's no difference between 2 and 3, so I leave that also in the interest of time. These two would be the same, I think, in this example. Yeah. Okay. Yeah. There's a question.
Can you explain how it's not why you have not false for R?
Can you speak up a bit? So can I explain why? What?
Why did you false for R?
Maybe because I made a mistake, but I don't think I did. So so the point in this example is that we set Q to be true. Yes. And then I can delete this entire clause. I can delete this entire clause. I can delete this entire clause, and I can delete this variable. So the only thing I get is P. So because it's a unit clause, I need to decide on P, and the value for P is then true, and then I'm done. I don't have any constraints left. Yeah. And R doesn't really matter. So there are 4 hands in the room. That probably means that I made a mistake. So who wants to shoot first? Yes, you.
I think you meant false. Yeah, like unit clause with R. And why didn't you set it with R2?
I didn't. Oh, you meant in the step before. Yes. So the point was, and my scribbling is rather bad, so I have to take all of it away. So let's say again, we start with Q, the false. That was the one on the slide before, that we're done with that. And now we have the true. And if we do the true, we can delete this one. We can delete. So I don't know. I still don't get the question.
Take Q to be false, then the unit clause is R.
Oh, and I did the other one. I did the on the.
You only took R to be true.
Okay, so let's do the false side again. Yes, so we start with Q being false. Then we can delete the Q, can delete this Q, we can delete this Q, and we can delete this clause. And then the next step is R, you're right. Yes, that was your point. Sorry for that. Yes, indeed, you're right. And that was also the comments of the other 4 people. No. Oh, okay, good. So let's finish this because you're. I think I owe you an answer. So now we have to make R true, indeed. And if you make R true, then we get P and not P. Sorry, this is the wrong one. This one would be, and you get the not R left. No, sorry, was right. So you get the not P, and then we get a contradiction here. Yeah, I think that is now the answer that you. Okay, here is a question.
In the exam, are we going to have to show that that's sufficient methods, or will it be like just find a solution?
I hope that it will be clearly written down what you have to do. So which of the variants you have to write.
Okay.
Yeah.
But we will have to, it's like in the practice exam, right?
It's like in the practice exam where this attempt is done. Yeah. Okay. You had a different point?
Yeah, I'm not really sure if I understand this right, but if the result is that Q is true and P is true, then I have two models that fit this in the knowledge base, right? So R can be false and can be true. So if it would be a truth table, I would have two rows.
Yes.
That's good. Okay.
Yes. So the question was what does it mean that we don't have a value for R here in this list? And it basically means that there are two models. So if you would look at the truth table, there would be two rows. The one would be with P is true, Q is true, and R is true. And that would be a model. And the other one would be P is true, Q is true, and R is false. And that would also be a model. Yeah. Okay, so let's move on. Yes?
Will we get the code for this algorithm in this course?
No. The question was, will you get the code for this algorithm in the course? You have it in the course, but is your question about the exam or is it about?
Like just get to use it, not to write it from ourselves, but to use it.
You have the pseudocode. In the last week's slides, there is a pseudocode on the real one. It's exactly this algorithm. Yeah, not with the heuristics. The heuristics is what we did here, but the algorithm itself is really specified in the slides from last week or from Tuesday. Okay, so just a final comment with this. What you basically get is that instead of 2 to the power of n being the number of variables, we reduce this now to 1.618 to the power of n. And if you look at something like 50 variables, this already makes a huge difference in terms of performance. Yeah, so that's why we do this, because we really have efficient ways of deciding satisfiability now. Now I want to give an extension, but I also want to give us a break because we had a lot of time in the beginning discussing issues with the course. I would suggest we have just a very short break. If we could have a 5 minutes nature break and come back at 12, and then I have more time to spend on the material. Yeah, so let's be back at 12. Okay. Time flies. Shall we start again? Okay, so what can the people in who are not here in the room hear me properly? Can you quickly confirm that you can hear everything else all right? Yes, okay, thanks a lot. Okay, so up to now, what we've done, and the only thing that Davis-Putnam can do, the only thing that Davis-Putnam does for us is, given some formulae in closed normal form, is tell us whether there is a model or not, or whether there are more models. Yeah. So it's only an algorithm for what's called SAT solving. Yeah. In logic, of course, there are more tasks that you might want to fulfill. You want, for example, to know whether a specific fact, a formula, follows from what you have specified in the model, in the knowledge base. Yeah, that's something you also, with a database, you want to know whether something is true in a database or not. You want to get out all the students in a class, and you ask a query and you want all the students back. So Davis-Putnam can't do that directly for us, but what it can do, or what we can do, is for these other tasks to translate them into satisfiability in propositional logic. So that's a very useful thing. So remember this notion of entailment. The notion of entailment is that a sentence, basically, when we played around with the Wumpus world, we said, okay, but it follows that 2 is a safe space. Yeah, because we understand how the logic of the game is and what the historic information was. So we know that it's safe. How do we know? It follows from the knowledge base, and semantically speaking, it means that the sentence is entailed. Yeah, and formally, this is basically here, written down here. So something follows from a knowledge base, or is entailed. Formula alpha is entailed if it is true in all the models of the knowledge base. And then we write down this funny symbol here. The knowledge base entails alpha. That's a very important notion in logic. You will, as I said, you will get back to that in logic in sets, but also in knowledge and data, so later in the study. And this is related to the notion of satisfiability and unsatisfiability, as I've shown you before, and as we've now got a very powerful tool for. So how does it work? And going back to the Wumpus world, we identified the 3 models of the knowledge base, the consistent ones, that the worlds that are consistent with our assumptions about the game and the observations. And I say world, I mean interpretations of the world. So basically, this was the information we had. There's no information, no sensoric information in 1.1. There is a breeze in 2.1. And then we have possible assignments of pits in the worlds around. So the pit can be here. So we could have 3 pits around. We could have 2 pits around, and so forth. And only 3 of them are consistent with the knowledge base that we have about the rules. Yeah. So these are the red ones. And this one, for example, violates the rule that there must be an adjacent pit to a breeze. This one violates that if there is a pit here, then there should have been a breeze in 1.1, and so forth. Yeah, you can check all of them. And only the ones in red are the ones which are consistent with our rules. Is a question?
It might be a dumb question, but why is the middle one also inside the yellow circle?
It's in a yellow circle and not in the red circle. So the red one is the ones which we think are consistent with the knowledge base. So these are the models. And the yellow one, it's a good question, is the ones where 1, 2, the field 1, 2 is safe. Yeah. So now the question is, we said, okay, if we have this information about the rules of the game and we have the observation of 1.1 and 1.2 or 2.1, then we know that 1.2 must be safe. That was something we humans find absolutely logical. But now we want to show it and we want to define it semantically. And it's called entailment. It's entailed that this is a safe world. And how do you do that? Exactly the question now. Basically, what you want to check is that in all the models, this is true. Yeah. So if I take any of the three models, then 1, 2 is safe. There's a different way of thinking of that, and that's saying if I take the world, the set of all the interpretations where 1, 2 is safe, if that's a superset of the models, then it's entailed. It follows. Yeah. So basically, the yellow ones in the yellow circle are the worlds, the interpretations where 1, 2 is safe. So these are the 4 worlds where there is nothing here, no pit here. In all the other ones, we have a pit here, we have a pit here, we have a pit here, and pit here. So the ones outside the yellow ones are the non-safe ones. So that one would be the ones where unsafe. But we know that all of them are outside our models. None of them is a model. Yeah. So basically, you can do this in 2 ways. Check whether something is entailed. You can either check for all the models, is it safe? So is there something here or not? There's no pit. There's no pit here. There's no pit here. So we are done. We've checked that in all the models, there is no pit in 2, 1. Sorry, in 1, 2. Always get the coordinates wrong. So in 1, 2, there's no pit. You can also do it the other way around, that you say, okay, I have 4 worlds in which 1, 2 is safe, namely the 3 yellow ones, the 3 red ones, and the one included in the yellow circle. And because the red ones are a subset of the yellow ones, I think I've moved one too fast. Yeah, because the red one is a subset of the yellow one, entailment holds. Yeah, that explains the yellow one. And if you take something differently, if we say, for example, is 2, 2 safe, then we simply go to 2, 2 with this information that we have. So this is only with the information that 1, 1 has no sensoric information and 2, 1 has a breeze. Then we can't say yet whether 2, 2 is safe or not, because given this information, these are still our models in red, and these would be the ones where 2, 2 is safe. So there's no pit here, there's no pit here, there's no pit here, there's no pit here. Yeah. But the definition was that it must be the case in all the models. Yeah. In all the possibly consistent worlds with the assumption. But it's not the case, because we have 2 models, namely the ones down here, in which 2, 2 is not safe. Yeah. So again, we have 2 ways of checking it. We can go to all the models. That would be the way you do it via truth tables. We enumerate all the models, which are the ones in red, and then we check for each 3 of them whether the 2, 2 is safe or not, or whether there's a pit in 2, 2. And we would find a contradiction, because in the world down here, the one where my pointer is, 2, 2 is not safe. That's one way. The other way of doing things is that we can also take the brown circle here. This is a brown circle, is the one which has all the worlds where 2, 2 is safe. And we show that the red ones are not a subset. And I will talk about set theory next week. So but I think that you get the general idea. Yeah. Okay. So there are now 2 ways where we can basically define what entailment is. And now the question is, how can we calculate this? And what we have is a calculation for satisfiability. So the way to do this now is that we say, okay, suppose now that we assume that P12 is not true. So it's a thought experiment. So we have all our models, the red ones. And now suppose that there is a pit in 1, 2. What should happen?
There shouldn't be a breeze at 1, 1.
Exactly. So if there would be a pit in 1, 2, our models would be right. So this would be inconsistent with our models, with our knowledge base, because the knowledge base says there is no pit in 1, 2. And now if we say, but there is a pit in 1, 2, then this is a contradiction. Yeah? And this is what we make use of by now assuming that we have a knowledge base, and we assume the negation of what we want to prove and then we show that it's unsatisfiable. And the good news is that we have an algorithm for showing satisfiability and unsatisfiability, namely Davis-Putnam. So now we can reduce the entailment question to a satisfiability checking, and we can simply reuse our efficient SAT solver. Yeah. So basically, there is a theoretical result, and that shows that a sentence alpha is entailed by a knowledge base KB, given this nice semantic symbol here, if and only if I take the knowledge base and I also take the clause, which is the negation of what I want to prove, and I show that it's unsatisfiable. So attainment on the one side and unsatisfiability on the other side. You have to remember that. So it's a bit asynchronous. Yeah. So in order to show entailment, all we have to do is that there is no model that satisfies knowledge base plus the negation of the formula we want to show that it's entailed. Yeah. We can also really bring this into procedure, into an algorithm. Check it out. It's really not difficult. It's I think the last question in the worksheet is exactly about this. What you have to do is you have to translate the knowledge base into closed normal form, because of course Davis-Putnam can only do closed normal form. You have to translate the negation of what you want to prove into closed normal form. Then we have to add these two closed normal forms. They're still in closed normal form because they're just sets. And then we have to apply our SAT solver. And if the SAT solver returns with a model, then we are not entailed. And if it returns with unsatisfiable, then we know that R is entailed. Yeah. Okay. So this is now sort of a means for using this efficient and optimized proof for SAT solving, also for entailment. And entailment is a very important notion in logics, because it gives you in principle everything that follows from the knowledge you have. And that's a very rich and powerful notion. Let's look at some of the properties of logics in a bit more detail, and about the reasoning tasks. And this is what I just explained to you. So a sentence is entailed by the knowledge base if it is true in all the models of the knowledge base. And this was the semantic side. Yes. Remember, we made the difference between the syntax, which is just the structure of the well-formed sentences. That's the easy stuff. Then we have the semantics, and the semantics is basically a mathematical system that tells us which of the formulae are actually true, consistent with my knowledge base, and what does it actually mean. So that's about the meaning, the semantics. Yeah. So the first notion here is about the meaning of the knowledge base and the meaning of the things I want to have it proven, have to follow from the knowledge I model. Yeah. The second thing is this thing, and that is means something completely different. So we have the difference between this symbol, which is semantic, and this symbol, and this one is about the meaning, and this is about the algorithm. That's a very important distinction. Yeah. So basically, the algorithm tells us that if I take the DPLL algorithm, Davis-Putnam, and I give it as input the knowledge base and the negation of the formula I want to prove. So this wiggled sign is a negation sign. Sorry, it's a bit inconsistent, but that's also one of the ways of writing down the negation. It should be, let's see whether, yes, so this should be this sign. Okay. And if Davis-Putnam comes back for this with unsat, then we have proven that this sort of logically follows from, that R follows logically from the knowledge base. Yes?
Sorry, but could you say one more time what is the difference between one with two dashes?
Okay, yeah, the question was whether I can explain once more what the difference is between the one with the two dashes and the one with one dash. Basically, the one thing is what I've defined sort of in mathematical terms, in formal terms, what the meaning of a formula is. Yeah. And the second thing is what my algorithm does. Yeah. And of course, and that's what the next sentence down here says, of course, we want to do these two things to be the same. Yeah. But if I make a mistake in my Davis-Putnam, then this thing does something differently. And I will show you an algorithm that is very efficient and very good and very impressive for set solving, but it doesn't do the same things. And that's can be something we're happy with, but it can also be a problem. Yeah. And why is this the case? Or what do we want? Actually, we want these two things to be the same. So these are very important notions of logic. So you will see that back in any logic course you have, is that we want the calculus to be sound. So that's basically the correctness of the algorithm. So if my algorithm says, yes, I believe that alpha follows from the knowledge base by my algorithm tells me, yes, this follows. Then I want it really to be true. I don't want me to tell some bullshit. Yeah. So this basically tells me about the quality of the output of my algorithm. Does it give the correct answer if I ask it, does alpha follow? Is to really safe? Then we want the algorithm really to be sure that it's safe, because otherwise my agent goes there and it dies. Yeah, we don't want that. The other direction is called completeness, and that means that if something follows logically, if I know that 2,2 is safe, then I want my algorithm to tell me. So it could be that my algorithm says, oh, I don't know whether 2,2 is safe or not. I cannot tell you. Yeah. So the first thing is that it should say that if it says this is a safe place, if that comes back from my Davis-Putnam entailment, then it should be safe. I should be able to trust the output. But also, if it says, I don't know, even if it could know, so maybe we would say, okay, 2,2 is safe, but I have written a bad algorithm, and it doesn't find out that 2,2 is safe. It could say, I don't know, and that would then be an incomplete algorithm. Yeah. So you want both. You want the algorithm to be sound, so that it gives you the correct results, and that it gives you all the correct results. That's basically the way of looking at it. And then termination is also a useful thing. Basically tells you that your algorithm will eventually finish. And there are logical formalisms like first order logic, again, something you'll see in next year. And it has a sound and a complete algorithm, but it's not guaranteed to terminate. So you simply don't know whether your algorithm hasn't given you the right answer yet, or whether it will never do. So in that sense, this is an important property to have in a proposition logic. We do have it. Yeah. And in an advanced course, you will prove why this Davis-Putnam is a sound and complete method and why it terminates. Yeah. It's not rocket science. You just know that you have a finite number of variable assignments you can have. So the algorithm will never work infinitely long. Yeah. But there are many logics and languages where this is not trivially true. Yeah. So you might have algorithms where you have infinitely many or structures of infinite size. And then to show termination is a big problem. Yeah, it's difficult. That's what we logicians do. And that's what you have to understand if you want to work with knowledge and logics in AI. Yeah. So these are important notions that I just wanted you to have seen and to understand. So the one is basically whenever my algorithm says that a place on the board of Wumpus is safe, it is really safe. The other one is the second direction is the completeness, is that whenever there is a safe space on the board, I want the algorithm also to say that it's safe and not say that it doesn't know. And the third thing, that it does so in finite time. Okay. So basically, we've now all the methods we've seen are based on the search for models. Yeah. And I think you've seen by the example that this can be done in relatively clever ways. So you do a depth first search and not a breadth first search. You do redundancy so that you don't do things again and again and again. And we apply the heuristics to choose for the best variable to split on, and so forth. And that leads us to the Davis-Putnam, and there are different algorithms, but the Davis-Putnam is really on the model searching side, the prominent one, and it's complete. So basically, it gives us always the correct answer, and for everything we want to be proven, it really comes back with an answer. So it's sound and complete. But there are also algorithms, particularly if you have more variables, because remember, we're still incredibly, we have an enormous amount of nodes that we need to check, or partial assignments. It's still 2 to the power of, or 1.6 to the power of 50. And if you try that on your calculator with 1,000 variables, so 1.6 to the power of 1,000, it will make your machine explode. Don't try it. Now you can try it, it's safe, but it won't be very useful. And of course, this means that if we have a difficult problem in propositional logic, the algorithm might take a couple of thousand years. And who wants a Wumpus world or a Schnapsen engine that takes 1,000 years to come back with an answer? So there are approaches where we say, okay, but all we need, think about it, all we need is to find one solution. We only want to find, for example, for entailment, we want to know whether it's entailed or not. And if we find a model, we know already that it's not entailed. So it might be good enough to find a model, even if we don't find all of them. Yeah. That would be the case if we are incomplete. If we're incomplete, we search for a model as quickly as possible, but we might not be sure that we find all of them. Yeah. That's the notion of incompleteness. And it's a very powerful one. And it brought people to the idea of a greedy SAT algorithm. And it's like in the search algorithm from the first week, we might not be optimal. We might not find all the solutions. Yeah. And how do you do that? You basically guess a variable assignment. I just say, okay, I start with P is true, Q is false, or all of them be true. Yeah. So that would be the first step. Random assignment. Yeah. So here we take some random assignment. Okay. And the chance that this really is a solution is in many problems not very high. But so we can check how good it is by just counting how many of the clauses does it satisfy, yeah, or violate. Yeah. And then basically what we do is, if we would change one of the variable assignments, so we had P, Q, and R, and I said, okay, let's start with all of them true. And then we could just say, okay, let's try out what happens if I make P false. Yeah. And then we could check in how many of the clauses are now true. Does it improve my search? And you see it already coming. It's a little bit like hill climbing, yeah, where you search for, oh yeah, but what is the next step? It's the greedy search algorithm, where the next step I check for, oh yeah, what is the best one? The heuristics would be counting the clauses that are now satisfied, the possible branches, so the actions I could take, the transitions, would be flipping one of the variables. And then I just check which of the flips of the variables would improve my satisfiability, my partial satisfiability the best. And I would just take this one and then I would search for the next one. So it basically is a hill climbing algorithm where the heuristics is the number of clauses that are satisfied. And then, of course, with hill climbing, we know that we could end up in this local maxima, so where we can't improve anymore, but also we haven't found a solution yet. And then basically, if you haven't found a solution and you can't improve, you throw it away, your assignment, and you restart again. So here's basically the algorithm that says you flip a maximum number of clauses, of literals. You check whether you found a solution. If after X flips you didn't find the solution, you throw everything away and you restart. Yes?
What if there's no solution? How many retakes do you do?
If there is no solution, is the question, what happens then? You stop after some finite time because it doesn't really make sense to go on forever. But that's the interesting case. Can you, if you stop and say, I didn't find, can you give the answer it's unsatisfiable? No, you can't, because you simply didn't find it, possibly. It could be that there is none. But it could also be that your algorithm was simply, you stopped because you haven't explored the whole search place. And what does that mean? Your algorithm is not complete, because it could be that there is a model that says, okay, but here is a solution, but I haven't found it yet because I have searched in different places in my assignment space. Yeah. So it's a very useful algorithm to, if there is a solution and you find it quickly by this random, it's a sort of a local search with restarts. That's what you could call it. Very useful in many applications. If you have, if the chance that you have a model is high, then this makes a lot of sense. But if you have just one model, for example, it's not a good approach. So it depends on the problem whether you want this kind of approaches, and you can never give a guarantee that my algorithm stops. Does it stop because there is no model, or does it stop because I didn't find it? And that's exactly what this notion of incompleteness means, that I have now a very powerful algorithm. This is the algorithm here. But it does very similar to what we wanted to do, but not really. Yeah, and that's this notion of incompleteness, and it can be very useful. But in principle, this is exactly what, as logicians, we try to understand. We want a mathematical system that tells us the notions of meaning formally. We want an algorithm that calculates that, and we want to understand whether they do the same thing. And propositional logic, let me tell you, is the most simple logic that you can think of. And it's, in this case, everything is fine. We understand, we have good algorithms, we can implement them easily, we can optimize them. All the optimizations we have are also sound and complete. We've proven that. But as soon as your languages become more difficult, as soon as you, for example, move to graphs, if we now want to model knowledge graphs, the notion that Frank talked about a lot in the first period, if you want to model that, things become far more messy and complicated. Yeah? And that's exactly what I want to get into now in the last 15 minutes. And the good news is the one in yellow and red up there is not relevant for the exam anymore. Yeah, so we don't have any way of practicing. All the material before we practiced. I really want you to remember these notions of soundness, completeness, and the differences between the semantic entailment and the inferencing, so the algorithmic one. So I think that is something that I can ask you to do until next Tuesday, to simply remember and try to understand from the way it is explained. So there might be a question, but more sort of knowledge question and nothing to calculate with in the exam. But what comes now is sort of a step up for the fourth practical. So the practical that Jan Christoph published today for next Friday is on adversarial search. So that's basically minimax and alphabetic pruning that you have to play around with and implement. And the week after, we do something with logic. So there's still a week to go. So I'll talk about this also next week, Thursday in the lecture. And then we try to sort of find out what kind of way we can, how can we model the game of Schnapsen in a logical way. So that may be a good moment to also talk about next Tuesday. So next Tuesday, we have a lecture scheduled at 11, but there will be no sort of lecture in the classical sense, but it's still, it's a one opportunity for you to ask questions, to get things explained again, if that helps. It's a bit, it could have been maybe better scheduled because the exam is then later in the day. So you have little time between this question and answers. You really need already to be well prepared. Don't leave it too late. And the idea is that I can explain some of the questions from the quizzes if you want me to. Yeah, so the quizzes are relatively close to the exam in terms of the way the questions are asked and also the distribution of questions and so forth. Practice them, and if you think, okay, but this is a nuance I don't really understand, then we can do that next week, and maybe we go through another Davis-Putnam proof if you want, or we any question next week. So there will be no new material next Tuesday, but just sort of helping you with preparing for the exam. Let's see the question.
The tasks. For example, if we do the logical tasks, the steps can be correct, but at the end, it's possible that we can mix and write something that is incorrect. But although the whole process was correct to the last step, and will we also get the points for the steps, or will there be just check if the answer is correct?
So the question is, if you have a more complex question that also has more points, whether only the end result will be checked, and if you have in principle all the intermediate steps right, but then an error at the very last step, whether you will get 0 points. So the ambition is, I cannot promise you, but the ambition is that those questions will have some intermediate answers that you should give, and so that you also get intermediate points for those that we have automatically checked. So if there is an open question that we, then of course you will get the intermediate points anyway. But if there is an automatic one where there's only one answer, and then we expect you to be able to also do the whole step correctly or not. But these should normally be questions that have fewer points. So it's not so that you have one huge one with 20 points out of 40, and then you have either you get it or not. That would be stupid. We try to avoid that. I hope it helps a bit. So what we're now stepping towards is a new logic. So we have looked at propositional logic, and all we could do there was take statements that could be true or false, and we combined them with these operators of and or, an implication, and negation. Yeah. So it was always about talking about things, about statements, about truth. Yeah. So that's what a proposition is. And combining statements about about propositions into complex formulae. Now, if you want to model more things of the world, you want also to model relations between instances, between people. So differences, there are also differences in modeling. For example, I have you as students in the room, but you also, I mean, I can talk to you as a sort of the group of students, and you have properties as groups of students, but you also have properties individually. So you all follow a class, so that's a sort of the joint property of the class of students in this room, but you have different birthdays, most of you. Yeah, so or different social security numbers. So these kind of things are possible to model and to work with in propositional logic. What we want to do instead is to come to a notion of knowledge graphs, where you want to represent these kind of things. So you want to say, okay, there is some person John, and this person is a professor, and we have also an undergrad student Ben, and you see already that there is the sort of the distinction made between the boxes with dots around, so the dotted lines, and those would be the ones that we call an individual. We want to model the individual, but it's related somehow to a class, maybe all the professors in the room or something, or that we know. And then we want to also somehow specify properties of professors we know, so that not every professor is also a person. Yeah, and every student is a person, and every undergrad is a student. Yeah. So if we now would have this type of information that I think is a relatively standard information that you would get out of a database with some schema, as it's called. So this thing, for example, would be part of a database schema that professors are persons. So if you now have a query to the system, so if, for example, if I would ask, give me all the persons, can someone tell me what the system should return? Ben and John. Yes. Yes. So how would you think a computer should say that Ben and John are the persons here? It has to go back the lines. So does some graph reasoning. Yes, that's a good one. Yes, there's a, yeah.
That's the follow the kind of statement to which is a statement and then
Yes, so it follows the statements, the is-a statements and the kind of statements. Exactly. But it's not just following this. So it's not just a sort of searching for a path, but it's also in a way understanding what these things are meant to stand for. Yes. You have a question here or point?
Basically, take the smallest elements of the largest group, which is the largest group is people or persons, and the smallest elements are the actual people in that group. Right.
Okay, can you
It's a
repeat?
subset. Students are a subset of persons. Professors are a subset of
Okay,
persons.
that's a
And then take
yeah.
the smallest element that is inside the person category.
So I don't understand what you mean by the smallest element, but I thought I liked a lot what you said about person and students are in principle a subset of person. So basically what, in another way of saying this, because we don't have really a notion of set theory yet, means that whenever something is a student, it should also be a member of the group of persons. Yeah. So you have a class of persons and you have a class of students, and everything that's in this class of students must also be in the class. Basically, what you've just been doing is that you've assigned, what we've been doing is that we've assigned a formal semantics to this. Yeah. This is nothing else but some kind of syntactic way of stating something about the relations between students and courses and so forth. And I wrote this as a graph, but I could also write it in a different way. So I could have also written down, let me write this one here on the top very quickly. I could also say, said a person holds, that's the relation between the two, and then degree. Yeah. And so that would be one way of writing this down. It would be called a triple. It's a sort of a part of a part of the graph, which is two nodes and the edge in between, and the edge has a label. The label of the edge would be holds, and then the name of the nodes would be degree and person. And what we've now realized is that there are some special ones in here. Because in a way, nobody has spoken about the teacher's relation. We've spoken about the kind of, which you interpreted as a subset relation. So the one is a subset of the other. And we also have the special one that is our relation. Yeah, which is also one where you would say we have an instance, one object, and it's part of a class. It's a sort of, we have a group of people, you know, a group of students, and then we have one specific one, he down here or she down there, and they are in this class. So there are two different things. One is one individual, and the other one is a group of things. Yeah. So we have in principle identified a logic. Yeah. Because what we want to have is we want to explicitly specify information about this, the world. We do this in a graph format, and we give it some syntax. So this would be the syntax. And now the next step was that we assign formal meaning to some of the vocabulary. Yeah. So basically what we now realize is that these things, the is-a, has a specific meaning. It's like the or in propositional logic. It's exactly the same thing. It's an operator in my logic. And the same is the kind of one, which is also one. They're different. They have different meanings, but they are exactly like the negation sign in propositional logic. Yeah. So basically our language that we're going to design consists of nodes in the tree, in a graph, labels in a graph, and triples that we can build out of those nodes, edges, and nodes and edges. And for some of the labels of the edges, we want to give some special meaning, like we do for the and for the or, and for the negation sign in propositional logic. Yeah? That's going to be the logic of knowledge graphs, and the entire course of knowledge and data is dedicated to this. I only want to be very quick here. We have 2 minutes left, so I have to be very quick. The main idea is that this whole knowledge graph is often also called a notology, because it also specifies relation between really conceptual entities in the world. So for example, that you say professors are persons. That sort of doesn't only say something about edges in a graph, but it says something about the world, specific classes of the world. And that's what you do in an ontology. An ontology is an explicit specification of a shared conceptualization that holds in a particular context. What does it mean? It must be explicit, it must be formal, it must be mathematically defined, machine interpretable, because we do computer science here. It must be shared, so it must be something that we jointly understand. So I show you my knowledge graph and you understand what it means. It must be a conceptualization, so, and not all the conceptualizations are the same. So if we, for example, think of lion, that could be the class of all the lions, but it could also be a species in the representation of all the species of the world. And these are conceptually two different things. So there are different ways of conceptualizing the world. And in an ontology, you do it in one specific way. But it's also context dependent. So whatever way I want to apply this ontology, I have to build a different one. Yeah, so there is no, we're not stipulating truth, but we are sort of giving one way of interpreting it in a way that it can be understood by a machine and in a way that can be shared also, for example, on the web. And the last thing I want to show you is here, for example, is an example of the language that you will learn in knowledge and data. It's called RDF. It's a resource description framework. The nodes in a graph are called resources. They are anything. So there could be you, there could be a website, there could be an idea. You call it a resource, can be everything. And then we relate those things with triples. A triple is basically something that is called a subject, a predicate, and an object. Yeah. And then we assign meaning to those operators. So for example, the one which was called in the knowledge graph that we saw was called ISA. Yeah, that basically would be called RDF type. The RDF is just in the description of the vocabulary that we're defining, like the conjunction sign and the disjunction sign. And as I said, this is like the operators. And we're going to see next week how we can combine those by rules in order to derive new facts. So this will be our calculus. We've seen the semantics. The calculus says that if you have, and this is what we've done in principle in the example just before, that if we have a ISA statement, so if Ben is a teacher and we have teachers are humans, then I can derive that Ben is a human or a person. Yeah? And this is the kind of reasoning that we do with these kind of graph languages. So in that sense, it's exactly the same as we've done with propositional logic, but with a different semantics and with a different reasoning system. And we're going to do this next Thursday. And I really hope that that the exam is okay and that it's fair. I have a last slide, but it's not coming, so it will be here. Next slide, last slide. You can already pack before I find it. Really, I hope everything goes right. I will help you next week. Yeah, there we are. So finish the second practical before tomorrow noon. Go to the worksheets again. Do the practice exams. We go through them on Tuesday morning. Take the exam. Good luck for it. There will be no working groups for the week after the exam. So some of them is Wednesdays next week. On Monday you still have the one, but then afterwards the Wednesday to Monday cycle doesn't go through. There's no working group. Great. And then we go on with this. Thanks a lot. Bye-bye.
Are we gonna have a lecture next Tuesday on day of the exam?
Yeah, there is a sort of question answer session where I help with the exam preparation. Okay. And if you think I don't need it, you don't come. You're welcome.